Now I am going to start module 3 of chapter 7. This module deals with application of Fourier transform to partial differential equation. In this regard, I want to mention that Fourier transform is a general transformation. Many other transformation like Laplace transformation, Mellin transformation, Hankel transformation can be defined in terms of complex Fourier transformation. Therefore, it is relevant to discuss about the application of Fourier transform to partial differential equation. In this module, we shall solve the Laplace equation, heat equation and wave equation using Fourier transformation method. Now we are going to slide show. First we shall start with Laplace equation. The Laplace equation in Cartesian coordinate system is given by del 2u del x square plus del 2u del y square equals to 0. Here we have considered infinite range for x and y is greater equals to 0. We have also the initial condition for u at t equals to 0 is equal to fx, and we also have u xy tends to 0 as y tends to infinity. We have u del x both quantity tends to 0 as mod x tends to infinity. Since x has infinite range of values, we take complex Fourier transform of the given equation with respect to variable x. So, we multiply the Laplace equation with e to the power I xi x and then integrate over x from minus infinity to plus infinity. The first term gives minus xi square u bar xi y and the second term is plus integration minus infinity to plus infinity d2u dy square e to the power I xi x dx equals to 0. Here xi is the transformed variable and the dependent variable or u is transformed to the function u bar. So, u bar is now function of xi and y. If you look at the expression which is given by the integration, in this integral if we interchange the differential and integral operator, then it gives d2 dy square of integration minus infinity to plus infinity u into e to the power I xi x dx. So, that is nothing but u bar. So, the second term in the expression is d2 u bar dy square and the first term is minus xi square u bar equals to 0. Now, this is the resultant equation. So, this is an ordinary second order differential equation in u bar and the solution of this equation can be written easily. It is a into e to the power xi into y plus b into e to the power minus xi into y, where a and b are arbitrary constants. Now, to get the bounded solution, u bar should have the functional form a into e to the power minus xi into y for xi greater than 0 and u bar equals to b into e to the power xi y for xi less than 0. Thus, for any xi, we can write the solution in the form u bar is equal to c into e to the power minus mod xi into y. Now, to find the value of c, we need to apply the initial condition. The initial condition is given u x0 is equal to fx Now, if we apply the Fourier transform of this equation, that gives u bar xi 0 is equal to some function f bar xi. Now, if we use this condition to the solution, u bar equals to c to the power minus mod xi y, this gives the value of c is equals to f bar xi. Now, substituting the value of c in the general solution, our required solution u bar, which is function of xi and y, is equal to f bar xi into e to the power minus mod xi into y. Now, we have to find u as function of x and y. That means, from this solution in the expression for u bar, we need to apply inverse Fourier transform to find u as function of x and y. Now, to obtain u as function of x and y, we need to apply inverse Laplace transform of u bar. So, the formula is written here, u is equal to 1 by 2 pi integration minus infinity to plus infinity e to the power minus I xi x into f bar xi. And we have also substituted the value of f bar xi, which is written here, minus infinity to plus infinity f eta e to the power minus xi y e to the power I xi eta d eta, this. So, in the next line, this is equals to 1 by 2 pi minus infinity to plus infinity f eta d eta into integration minus infinity to plus infinity e to the power xi into I eta minus x minus mod xi into y d xi. In the second line, we interchange the order of integration. Now, we can evaluate the second integral, and the value of the second integral is 1 divided by eta minus x whole square plus y square. Therefore, our required solution u function of x and y is equal to y by pi integration minus infinity to plus infinity f eta d eta by eta minus x whole square plus y square. Now, we shall consider heat conduction equation, and we shall apply complex Fourier transform to find solution of this equation. So, the given equation is the heat equation, one dimensional heat equation in Cartesian coordinate system, which is given by equation 1, del u del t equals to kappa del t u del x square, where x lies between 0 to infinity, and this equation is satisfied with the given condition. This is the boundary condition, u at x equals to 0, t equals to u 0 for mod t less than capital T and equals to 0 for mod t greater than capital T. And we also have the solution is bounded, that means u tends to 0 as x going to infinity and mod t going to infinity. Thus, we have to solve the conduction equation together with the condition which are given by 2 and 3. So, first we take Fourier transform of the given equation with respect to t. Since t has range from minus infinity to plus infinity, we are taking Fourier transform with respect to t. So, for that reason we are multiplying the equation by e to the power I xi t and then integrate over minus infinity to plus infinity. the first term, if you look the left hand side of this expression, we are applying in the next line, we are applying the integration by parts. So, for that we are assuming e to the power I xi t as our first function. So, according to that rule, first function into integration of second function, that is u, over minus infinity to plus infinity, minus integration of derivative of first function. So, that gives e to the power I xi t into I xi, and integration of second function, that is u dt, is equal to the right hand side. Here we again interchange the operator integration and differential, then this is equals to kappa d2 u bar dx square, where u bar is the Fourier transform of u with respect to variable t, and we have the condition that u tends to 0. If you look back the condition 3, u tends to 0 as x tends to infinity and mod t tends to infinity. So, if you apply that, we get the term in the square bracket is 0. So, this term is 0, and the second term is minus I xi into, this is nothing but Fourier transform of u with respect to t. For this problem, we are denoting that by u bar. So, left hand side is minus I xi u bar equals to kappa d2 u bar dx square. So, it can be written in this form also, d2 u bar dx square plus I xi by kappa u bar equals to 0. Now, this is a second ordinary differential equation in x, and the solution of this equation can be written in the form u bar equals to a square root of I xi by kappa into x plus b into e to the power minus square root of I xi by kappa into x, where a and b are arbitrary constants. Now, we apply Fourier transform to the given condition. So, if you look at this condition, condition 2, this is the boundary condition. So, if we apply Fourier transform to that, it gives u bar 0 xi is equal to integration minus infinity to plus infinity u 0 e to the power I xi t dt. But we also have that the value of u is u0 within the interval minus t to plus t. So, outside that interval, the value of the integral becomes 0. So, the limits of the integration becomes minus t to plus t. So, after integration, we get its value is equals to 2 u0 sin xi t divided by xi. It can be written in the form also 2 u0 sin mod xi t divided by mod xi, and this form is applicable for both xi greater than 0 and xi less than 0. Now, if we look at the first condition of 3, which is u goes to 0 as x goes to infinity. So, in that condition, if we apply Fourier transform, we obtain u bar xi goes to 0 as x goes to infinity. Now, for xi greater than 0, we have square root of minus I xi by kappa is square root of mod xi by 2 kappa into 1 minus I. So, if we use that result, the general solution of equation 1 can be written in the form u bar equals to a e to the power minus x square root mod chi by 2 kappa into 1 minus I plus b e to the power x into square root mod chi by 2 kappa into 1 minus I. Now, using the condition u bar xi tends to 0 as x tends to infinity, it follows that b is equal to 0, because in this expression u bar, if b is there, then u bar will tend to infinity because of this term x. So, b cannot be a non-negative or non-zero number. So, the only option is b is equal to 0. Therefore, the general solution can be written as u bar equals to a e to the power minus x square root mod xi by 2 kappa into 1 minus I. Now, to obtain the value of a, we need to apply now the boundary condition u bar 0 xi equals to 2 u 0 into sine mod xi t divided by mod xi. If you apply this condition, this gives the value of capital A as 2 u 0 into sine mod xi t by mod xi. So, substituting this value of A, now our required solution becomes u bar equals to 2 u 0 sine mod xi t by mod xi e to the power minus x square root mod xi by 2 kappa 1 minus I. So, this is the solution for xi greater than 0. Similarly, for xi less than 0, we can obtain the solution in the form u bar equals to 2 u 0 sine mod xi t divided by mod xi e to the power minus x square root mod xi by 2 kappa into 1 plus I. Now, to obtain u as function of x and t, we need to apply inverse Fourier transform. So, this is the formula of inverse Fourier transform. So, u x t equals to 1 divided by 2 pi integration minus infinity to plus infinity u bar e to the power minus I xi t into d xi. Now, we break the interval into two parts. One is for negative values of xi and the other is for positive values of xi. So, in these two intervals, we substitute the values of u bar, and substituting these values, we obtain u as u 0 by pi integration 0 to infinity sine mod xi t divided by mod xi e to the power minus x square root mod xi by 2 kappa into e to the power I x into square root mod xi by 2 kappa minus xi t plus e to the power minus I x into square root mod xi by 2 kappa minus xi t, and this can be simplified to cosine function. So, in the next line, the term can be replaced by cosine function, which can be seen in this slide, the last line of this slide. So, this is our required solution. Now, we are considering Fourier transform to find solution of wave equation. Now, this is the equation, wave equation in Cartesian coordinate system. Del t u del t square equals to c square del t u del x square, where x has infinite range and t is greater than 0, and we have also the initial condition u at t equals to 0 is fx and del u del t at t equals to 0 is gx, and we also have u and del u del x tends to 0 as mod x tends to infinity. So, first of all, we take Fourier transform of the equation which is written in 1 with respect to x. So, after taking Fourier transform, the equation becomes d2 u bar dt square plus xi square c square u bar equals to 0, where u bar is the Fourier transform of u with respect to x. Now, the solution of this ordinary differential equation is u bar equals to a e to the power I xi c t plus b e to the power minus I xi c t, where a, b are arbitrary constants. Now, to obtain the values of these arbitrary constants, we need to apply the initial conditions. The Fourier transform of the initial condition gives u bar xi 0 equals to f bar xi and du bar dt at point t equals to 0 is g bar xi. Now, if we apply these two conditions in the general solution, we obtain a plus b equals to f bar xi and I xi c into a minus b equals to g bar xi. So, from these two equations, we can obtain the values of a and b as a equals to half f bar minus I by xi c g bar and b equals to half f bar plus I by xi c g bar. So, substituting the values of a and b in the general solution, here we obtain u bar as half f bar into e to the power I xi c t plus e to the power minus I xi c t minus I by 2 xi c into g bar into e to the power I xi c t minus e to the power minus I xi c t. We need to find the value of u as function of x and t. So, to obtain u, this is the time to take the inverse Fourier transform of u bar. Thus, we take inverse Fourier transform of u bar. So, u is equal to 1 by 2 pi minus infinity to plus infinity u bar xi t e to the power minus xi x d xi. So, this equals to half 1 by 2 pi minus infinity to plus infinity f bar xi e to the power minus I xi x minus c t plus e to the power minus I xi x plus c t d xi plus 1 by 2 c minus I by 2 pi integration minus infinity to plus infinity g bar by xi into e to the power minus I xi x minus c t minus e to the power minus I xi plus c t d xi. We know the expression for f(x). This is the inverse Fourier transform of f bar xi. So, f(x) equals to 1 by 2 pi integration minus infinity to plus infinity f bar xi e to the power minus I xi x d xi. So, in this expression, if you take the argument of f as x minus c t, so value of f x minus c t is equals to 1 by 2 pi minus infinity to plus infinity f bar e to the power minus xi into x minus c t. So, x will be replaced by x minus c t in this expression. Similarly, the value of f x plus c t can be obtained from the expression of f x by replacing x by x plus c t. So, the expression for x plus c t is given here, and we also have g eta This is inverse Fourier transform of G bar. So, G eta is equals to 1 by 2 pi minus infinity to plus infinity G bar xi e to the power minus I xi eta d xi. And in this expression you can see that integration x minus ct to x plus ct g eta d eta is equals to integration x minus ct to x plus ct d eta, and this is the expression for g eta. So, this equals to 1 by 2 pi minus infinity to plus infinity g bar zeta e to the power minus I xi eta d xi. So, this equals to 1 by 2 pi. Now, we interchange the order of integration. So, it is minus infinity to plus infinity g bar xi, and this is x minus ct to x plus ct e to the power minus I xi eta d eta into d xi, and we can find the value of this integral, and value of this integral becomes here, which is written here, e to the power minus I xi into x minus ct minus e to the power minus I xi x plus ct divided by xi. So, the value of the integral x minus ct to x plus ct g eta d eta is shown here in equation number 4. Therefore, the solution u x t can be written in the form u x t, which is given by equation 2. It can be represented in the form also half of f x plus ct plus f x minus ct plus 1 by 2 c integration x minus ct to x plus ct g eta d eta, and this is famous D'Alembert solution of wave equation. Thus, it is possible to find the D'Alembert solution of wave equation using Fourier transform method. Thus, in module 3 of chapter 7, we have learned how to find solution of Laplace equation, heat equation and wave equation using complex Fourier transformation. There is also sine Fourier transformation and cosine Fourier transformation which can be applied to find solution of above systems. Those derivations are available in e-text. This method can be applied to find solution of integral equation. It has application in statistics also. This method is very useful to find frequency of a signal in electrical engineering. Now we end this module.